Wireless power, I mean, it really does feel like magic, doesn't it? You put your phone down on a pad, and poof, it just starts charging. But as this tech gets more and more powerful, showing up in kitchen appliances, tools, even our cars, a really important question pops up. How do we actually know all that energy flying through the air is safe for us?
Right. That simple question, is it safe? Well, it has a surprisingly complex answer. And that's exactly what we're going to unpack today. We're going to dive into the rigorous, internationally agreed upon process that every single manufacturer has to follow to prove their device is perfectly safe.
So, to answer that question, international groups like the IEC got together and created a standardized playbook. And what we're going to do is break down the absolute core of that playbook, how they assess the direct effect of these electromagnetic fields on the human body. The stuff that really matters, like making sure there's no tissue heating or nerve stimulation.
Now, this whole safety process is built on a really smart trade-off. On one side, you have these conservative methods. They're easy, they're fast, but they make a lot of worst-case assumptions. On the other side, you've got precise methods, way more complex, slower, but tailored to a specific device. Think of it like a ladder. The goal is to prove you're safe, and you only need to climb as high up that ladder as you absolutely have to. So, here's our game plan for today. We're going to walk through that ladder, the official four-step process from the simplest check all the way to the most detailed one. All right, let's get into it. Okay, let's zoom out for a second and look at the big picture. There's an international standard, IEC63184, that lays out a crystal clear flow chart for this whole thing. And that's the map we're going to follow, step by step. And here it is, what I've been calling the ladder of certainty. It's brilliant, really. A company can stop at any rung on this ladder as soon as they prove their device is compliant. You start at the bottom with the easiest, most cautious check. If you pass, you're done. Awesome. If you don't, well, you've got to climb to the next rung, which gets a little more precise and a little more complicated.
But before we even put a foot on that ladder, we need to know what the destination is, right? The ultimate goal, the finish line for every step, is to prove you comply with something called basic restrictions. These are the fundamental, non-negotiable safety limits that are based directly on known health effects. This is the ground truth of safety. Okay, let's start climbing. We're on the first rung of the ladder. This is the simplest, quickest, and most straightforward check of them all. Step 1 really just boils it down to one simple question. It's the easiest way for any low-power device to get a safety pass. You don't need any fancy field measurements. All the manufacturer has to do is check their device's maximum power against a super conservative, predefined limit. So, what does low enough actually mean? Well, the standard lays it right out in this table. For example, let's look at a device used by you and me, the general public. The basic safety limit for tissue heating is 2 watts per kilogram. This table shows that if the device transmits less than 20 milliwatts, which is tiny, boom, it passes, instantly. No more testing needed. It's a simple pass-fail. But if it fails, it's on to the next step. So what happens if your device is a bit too powerful for that simple check-in in step 1? Well, then you have to climb up to step 2. And this is where we stop looking at just the device's power and start actually measuring the electromagnetic fields it creates in the space around it. And here, we have to introduce a new concept, reference levels. Now think of these like a safety bubble. They're not the actual health limits inside your body. Instead, they're limits for the fields outside your body, and they're set really low to be extra cautious, just to make absolutely sure those internal limits, the basic restrictions, are never ever broken. The process seems straightforward, right? You measure the fields, you compare them to the reference levels. But here's the catch. Wireless power fields are usually very focused in one small area. And these reference levels often assume the field is hitting your whole body uniformly, which is a worst-case scenario that's not very realistic. So a device might fail this test even if it's totally safe, and that's what brings us to the next step. So let's climb up to step 3. This is where things get a lot more sophisticated. We are still measuring the field on the outside of the body, but now we're going to analyze it in a much smarter, more realistic way. So here's the key. Step 2 can be way too conservative because it assumes the worst. Step 3 acknowledges the reality of wireless power, that it uses a highly localized, rapidly changing field, and to handle that, it uses a really clever corrective tool called a coupling factor. This step is so much more nuanced by looking at not just the field's strength, but also its gradient. How quickly it changes over a short distance. We can apply this special coupling factor. This factor basically lets us translate that external field measurement into a much more accurate prediction of what's happening inside the body, all without ever having to measure there directly. It's a smarter, more refined way to get to the truth. But what if a device, even with this smarter assessment from step 3, still hasn't passed? Well, then we have to climb all the way to the top of the ladder, to the final, most complex, and most precise step of all, directly evaluating the field's impact inside the human body. And this brings us to the key metric for heat effects, SAR, which stands for specific absorption rate. We're not dealing with proxies or conservative estimates anymore. This is the real deal. It's a direct measure or calculation of the rate at which energy is literally being absorbed by body tissue, and it's measured in watts per kilogram. At the very top of the ladder, you've got 2 paths to prove you're safe. The first is physical measurement. You use something called a phantom. It's basically a model of a human head or torso, and it's filled with this special liquid that acts just like human tissue. You stick a tiny probe in there and measure the SAR directly. The second path is a super complex computer simulation, using a detailed anatomical model of the human body to calculate everything numerically. Both of these methods give you a direct answer that you compare right against those fundamental basic restrictions. You know, the standard itself sums it up perfectly right here. What this is really saying is that step 4 is the ground truth. It's the most accurate you can get because it strips away all the what-ifs and conservative guesses from the earlier steps and just looks at the direct, real-world impact. So what's the big takeaway here? Well, it's this tiered 4-step approach, this ladder of certainty. It provides a flexible and really robust way to make sure every single wireless power device is safe, balancing simplicity with precision. It protects all of us without making every low-powered gadget go through the most expensive, complex testing imaginable. And it leaves us with a really interesting thought. As this technology evolves for electric cars or even medical implants, how will this very ladder need to adapt and evolve right along with it? Thanks for watching.